There is a simple test to gauge how radically different an astronomical object is from anything in everyday experience. The test consists of taking its physical properties and translating them to human scales. With most astronomical objects, the result is simply a large number, something that produces awe due to its magnitude, but does not challenge any fundamental intuition about how matter works. With neutron stars, the result is different. With neutron stars, the translation produces statements that the brain instinctively rejects as impossible, yet they are rigorously correct according to the best physics we possess. Consider this. A typical neutron star has a mass between 1.4 and 2 solar masses. The Sun has a mass of 2 times 10 to the power of 30 kilograms, approximately 330,000 times the mass of the Earth. The neutron star compresses that mass into a sphere approximately 20 kilometers in diameter. The Sun's diameter is 1,400,000 kilometers. The Earth's diameter is 12,700 kilometers. The diameter of a neutron star is comparable to that of a medium-sized city, to the radius that separates the center of Madrid from its periphery, to the distance a car at highway speed covers in 12 minutes. In that city-sized sphere, more mass than that of the Sun is compressed. The resulting density is between 10 to the power of 17 and 10 to the power of 18 kilograms per cubic meter. For that figure to have any meaning, it is useful to compare it with known objects. Water has a density of 1,000 kilograms per cubic meter. Iron, one of the densest materials in everyday experience, has a density of about 7,800 kilograms per cubic meter. The atomic nucleus, the densest structure that exists in ordinary matter, has a density of approximately 2 times 10 to the power of 17 kilograms per cubic meter. Neutron stars have densities comparable to or higher than those of the atomic nucleus. They are not objects with nuclear properties in their interior. They are, to a certain extent, a single city-sized atomic nucleus, a teaspoon of neutron star material if you could take it out of the star without it immediately expanding in a catastrophic explosion, would weigh approximately 1 billion tons. That is more than the combined weight of all the humans who have ever lived on Earth, plus that of all current land animals, compressed into the volume of a sugar cube. The gravity on the surface of a neutron star is approximately 2 times 10 to the power of 11 times the gravity of the Earth's surface. A 70-kilogram person on the surface of a neutron star would weigh approximately 14 billion tons. The temperature on the surface of a newly formed neutron star exceeds 1 million degrees Kelvin. The magnetic field of some types of neutron stars reaches 10 to the power of 15 Gauss, 1 trillion times more intense than the Earth's magnetic field and 100 million times more intense than the most powerful superconducting magnet that human engineers have ever built. Each of those statements is experimentally verifiable. Each of them is supported by decades of observations, by theoretical models that predict behaviors that are later confirmed, by the consensus of thousands of physicists and astronomers who have dedicated their careers to understanding these objects. And yet, the image that emerges when they are all taken together is that of an object that seems designed to violate the most basic physical intuitions. Neutron stars are not simply large or dense or hot objects. They are frontiers of physics, places where the laws of nature operate in regimes that no laboratory experiment can reproduce, where general relativity and quantum mechanics and nuclear physics converge in ways that science still does not fully understand. They are, in that precise sense, stranger than we ever imagined, and we continue to discover with each new observation that even this falls short. How an impossible object is born. To understand what a neutron star is, we need to understand how it forms. And to understand how it forms, we need to understand how massive stars die. Because neutron stars do not emerge from nothing. They are the result of one of the most violent events the universe produces, and their formation is inextricably linked to the previous history of the star that generates them. A massive star with a mass between 8 and approximately 20 solar masses on the main sequence spends most of its life fusing hydrogen into helium in its core. This process, which can last between 10 and 100 million years depending on the mass of the star, releases energy that exerts outward pressure that exactly balances the gravitational pressure that the weight of the star's gas exerts inward. It is a delicate and precisely calibrated balance, and it is called hydrostatic equilibrium. As long as the fusion fuel is available and the fusion process works, the star remains stable. The problem is that nuclear fusion cannot continue indefinitely. Each stage of fusion produces an element heavier than the previous one, and that heavier element becomes the new fuel for the next stage, from hydrogen to helium, from helium to carbon and oxygen, from carbon to neon and magnesium, from neon to oxygen and silicon, from silicon to iron, and here the process stops abruptly and definitively. Iron is the most stable element in the universe in terms of binding energy per nucleon. To fuse iron nuclei with each other and produce heavier elements, energy is not released. On the contrary, energy is required. Iron fusion absorbs energy instead of producing it. When the core of a massive star accumulates enough iron, in the characteristically brief time of a few days, the energy source that maintained hydrostatic equilibrium is abruptly cut off. Radiation pressure disappears, and what remains is gravity, acting unopposed on an iron core of approximately 1 solar mass, compressed into a volume the size of the Earth. What happens next occurs in a fraction of a second. The iron core collapses under its own gravity at a speed that can reach 25% of the speed of light. In less than a second, the core goes from being the size of the Earth to being the size of a city. During that collapse, the density reaches and exceeds nuclear density. Under these extreme conditions, a process occurs that under normal conditions is energetically unfavorable. Electrons are forced to combine with protons from the iron nuclei through electron capture, producing neutrons and neutrinos. Almost instantaneously, the core becomes a sphere of packed neutrons at nuclear density, what physicists call a proto-neutron star. This newly formed sphere of neutrons has enormous rigidity, neutron degeneracy pressure, a purely quantum effect derived from the Pauli exclusion principle that prohibits two identical fermions from occupying the same quantum state, opposes the gravitational collapse with a force that can stop the collapse if the core's mass is small enough. The collapse bounces. The outer layer of the star, which was still falling inward at relativistic speeds, meets this rigid core and bounces outward in the form of a shock wave of immeasurable proportions. The energy released in this process is approximately 3 × 10 to the power of 46 joules, a figure that requires a moment of contemplation. This amount of energy is approximately 100 times the total energy that the Sun will emit throughout its entire 10 billion year life. It is the energy released in less than a second. 99% of that energy is immediately carried away by the neutrinos produced during the collapse, which pass through the stellar envelope and escape into space almost without interaction, because neutrinos interact with matter with extraordinarily low efficiency. Only 1% of that energy is deposited in the stellar envelope, but that 1% is enough to launch layers of gas weighing several suns at speeds of 10,000 kilometers per second. The result visible from the outside is what we call a supernova, one of the most luminous events in the observable universe. What remains in the center, if the mass of the core does not exceed the Tolman-Oppenheimer-Volkoff limit of approximately 2 to 3 solar masses, is a neutron star. The physics of the impossible. What is inside? The interior of a neutron star is one of the most challenging places for theoretical physics, not because we lack ideas about what is there, but because the conditions are so extreme that no laboratory experiment can reproduce them. And the theories that must be applied, nuclear physics, quantum chromodynamics, and general relativity, have not been verified in that regime with any direct observation. What we know about the interior of a neutron star is a combination of solid physics, reasoned extrapolation, and, in some regions, grounded theoretical speculation. The outer layer of a neutron star, called the crust, is the best understood part. In this region, iron ions and other heavy nuclei organize into a solid crystalline lattice, held in place by the pressure of the free electrons surrounding them. It is, in structural terms, an extremely dense and rigid metal. The temperature in this region, although it can be millions of degrees Kelvin in a young neutron star, is low enough compared to the Fermi temperature of the electrons for the behavior to be that of a solid, not a plasma. As one goes deeper into the star, the density increases and the atomic nuclei become increasingly neutron-rich, first normal iron, then exotic isotopes with dozens more neutrons than protons, which under normal conditions would be highly unstable and decay in microseconds, but are stabilized here by extreme pressure. In the inner crust, at densities between 4 times 10 to the power of 11 and 10 to the power of 14 kilograms per cubic meter, the nuclei begin to release neutrons that form a sea of free neutrons around the crystalline lattice. This system, with free neutrons coexisting with a lattice of heavy ions, has no analog in any material we have studied in the laboratory. The free neutrons in the inner crust of a neutron star exhibit a property that causes theoretical physicists to dedicate entire years to its study. They are superfluids. Superfluidity, familiar in helium-4 at temperatures near absolute zero, is a state of matter in which viscosity is exactly zero, and the fluid can flow without any dissipation of energy, indefinitely, without any friction. In superfluid helium, this produces behaviors as strange as spontaneously flowing upward over the walls of the container, or the formation of quantized vortices that persist eternally. Inside a neutron star, neutrons form a superfluid at a temperature trillions of times higher than that of superfluid helium in the laboratory, because the density is so extraordinarily high that the transition temperature to superfluidity also rises extraordinarily. The consequences of this superfluidity for the observable behavior of neutron stars are measurable and have been confirmed in several observational contexts. Deeper still, at densities exceeding nuclear density, physics becomes genuinely uncertain. At those densities, individual nucleons, protons and neutrons could begin to decay into their most fundamental constituents, quarks. Quantum chromodynamics, the theory that describes the strong interaction that holds quarks together inside nucleons, predicts that at sufficiently high densities, quarks should become deconfined, forming what is called quark matter or a quark gluon plasma. If the core of a massive neutron star reaches those densities, it could contain free quarks, possibly organized into exotic phases with names reflecting their strangeness. Strange quark matter containing U, D, and Es quarks in approximately equal proportions, or kaon condensates, or color flavor locked quark superfluids. None of these phases have been directly observed. All of them are theoretical predictions consistent with known physics, extrapolated to unexplored regimes. And the distinction between them has observable consequences for the maximum mass of neutron stars, the equation of state governing their radius, and the gravitational waves they produce when two of them collide. Pulsars, cosmic clocks. In August 1967, doctoral student Jocelyn Bell, working at the University of Cambridge under the supervision of Anthony Hewish, detected a radio signal that did not fit into any known category. It was periodic, extraordinarily regular, with a period of 1 second and 337 thousandths, and it arrived from a fixed direction in the sky. The regularity was so precise that during the first few weeks, Bell and Hewish seriously considered the possibility that it was a signal of intelligent origin, and jokingly called the source LGM1 for little green men. The extraterrestrial explanation was quickly discarded when similar signals were found coming from other directions in the sky, and the correct physical cause was proposed a few weeks later by Thomas Gold and Franco Pacini. It was a rapidly rotating neutron star, emitting radiation from its magnetic poles like a cosmic lighthouse. The era of pulsars was born. Pulsars are neutron stars that emit beams of electromagnetic radiation from their magnetic poles. In most neutron stars, the rotation axis and the magnetic dipole axis are not aligned exactly as the Earth's rotation axis and its magnetic pole do not perfectly coincide. This misalignment causes the radiation beams to sweep through space with each rotation, like the beams of a signal lighthouse. If one of those beams points toward the Earth during part of its cycle, we detect a pulse of radiation with each rotation of the star. The frequency of the pulses is directly the rotation period of the neutron star. The first surprise of pulsars was their extraordinary regularity. The pulses of the first pulsar discovered, renamed PSRB 1919+21, arrive with a precision of parts in 10 to the power of 13, comparable to the best atomic clocks in the world. This regularity has a direct physical cause. The neutron star is an object of enormous rotational moment of inertia and with very little friction in its environment, so its rotation speed decreases extraordinarily slowly and predictably. Language purists might argue that atomic clocks are more precise, but millisecond pulsars, those that spin hundreds of times per second, rival the best oscillators humanity has built in terms of long-term stability. The second surprise was the diversity. The pulsars known today exceed 3,000, with rotation periods ranging from the current record of a few milliseconds to several seconds. There are pulsars that emit in radio, in X-rays, in gamma, in optics. There are pulsars with stellar companions and solitary pulsars. There are pulsars in binary systems with other neutron stars, with white dwarfs, with main sequence stars. There are pulsars that emit perfectly regular pulses and pulsars that show nulling, periods where the pulses cease completely for hours or days before reappearing without a clear explanation. There are pulsars that occasionally emit giant radio pulses, thousands of times brighter than ordinary pulses for periods of a few microseconds. The phenomenology of pulsars is so rich that a single chapter cannot do justice to its diversity. What makes pulsars scientifically valuable beyond their own study is their utility as precision tools for measuring other things. Observations of the arrival time of pulses from a pulsar over years or decades accumulate information about any process that modifies the time between successive pulses, the rotation of the star, its movement in space, the effects of general relativity on time in the vicinity of the object, the presence of stellar companions that gravitationally perturb the orbit, and the presence of gravitational waves that modify the metric of space-time through which the pulses travel. Pulsar timing experiments have produced some of the most precise tests of general relativity available, surpassing in some cases the tests conducted in the solar system with spacecraft and atomic clocks. Millisecond pulsars, stellar recycling. If ordinary pulsars are already extraordinary objects, millisecond pulsars take that extraordinariness to another level. A millisecond pulsar is a neutron star that rotates hundreds of times per second with periods ranging from approximately 1 millisecond to 20 milliseconds. The current record is held by PSRJ 1748-2446 AD with a rotation period of 1.396 milliseconds, which corresponds to about 716 rotations per second. The equatorial surface of this neutron star moves at approximately 24% of the speed of light. How does a neutron star acquire such an extreme rotation speed? The answer involves one of the most fascinating processes in compact object astrophysics: recycling. Newly formed neutron stars rotate fast, with periods from milliseconds to tenths of a second, but the emission of radiation over millions of years causes their rotation to progressively decelerate. A typical pulsar loses rotational energy at a measurable rate, and its period lengthens until, after about 100 million years, the neutron star has lost enough speed for the radio emission to cut off and the pulsar to become inactive from our perspective. But if that neutron star has a stellar companion in a close orbit, the story can continue differently. When the stellar companion evolves and expands its envelope as a red giant, the material it loses can fall toward the neutron star, forming an accretion disk. That material, as it spirals toward the surface of the neutron star through the accretion disk, transfers angular momentum to the star, accelerating its rotation gradually but continuously over millions or even billions of years. At the end of this accretion process, the neutron star has been accelerated again to extreme rotation speeds, now as a millisecond pulsar. The stellar companion, which donated the material during accretion, has been consumed until it becomes a low-mass white dwarf. The resultant system, a millisecond pulsar with a companion white dwarf in a nearly circular orbit, is the final product of stellar recycling. This recycling narrative was proposed in the 1980s and verified by multiple observations in the following decades. But the most direct and spectacular verification came with the identification of so-called low-mass X-ray binaries with active accretion, systems where we can observe in real time the accretion process that will eventually recycle the neutron star. In 1998, the X-ray satellite RXTE detected coherent X-ray pulsations in the system CXJ 180 8.4-3658 with a period of 2.5 milliseconds during a period of active accretion. It was the first time a neutron star was directly observed being accelerated by accretion to millisecond speeds, confirming the recycling mechanism with direct evidence. Millisecond pulsars have an additional property that makes them extraordinarily valuable. Their rotational stability is even greater than that of ordinary pulsars. The reason is that the rotation period is much shorter than that of young pulsars, and the rate of period decrease is also much lower, because they no longer have the intense magnetic field of young pulsars that efficiently dissipates energy. The result is that millisecond pulsars are the most precise cosmic clocks known, and their use in pulsar timing experiments has reached a sensitivity sufficient to detect perturbations in spacetime with an amplitude of 1 in 10 to the power of 15. It is at this level of sensitivity where pulsar timing experiments become low-frequency gravitational wave detectors. Magnetars, when the magnetic field becomes weaponry. In the catalogue of the most extreme objects in the universe, magnetars occupy a category of their own. They are neutron stars, but with magnetic fields that exceed those of ordinary pulsars by several orders of magnitude, between 10 to the power of 13 and 10 to the power of 15 Gauss, compared to the 10 to the power of 8 to 10 to the power of 12 Gauss of normal pulsars. To calibrate that number, the Earth's magnetic field is approximately half a Gauss. The magnet of a modern hospital's MRI scanner has around 10 to 20,000 Gauss. The most powerful superconducting magnet ever built in a laboratory reaches approximately 45 Gauss in sustained regimes. The weakest known magnetar has a magnetic field of 10 to the power of 13 Gauss. The difference between the world's most powerful laboratory magnet and the weakest known magnetar is 9 orders of magnitude, that is 1 billion times. Magnetars were theoretically proposed in 1992 by astrophysicists Robert Duncan and Christopher Thompson as a subclass of neutron stars that would form when the progenitor star had a sufficiently fast rotation during core collapse to generate an extreme magnetic field through a dynamo process. Observational verification arrived in the following years with the identification of 2 types of objects that turned out to be magnetars: soft gamma repeaters, sources that periodically emit bursts of soft X-rays and gamma rays, and anomalous X-ray pulsars, neutron stars that emit X-rays brighter than what their rotational deceleration rate can explain without an additional source of energy. What makes magnetars physically unique, beyond the magnitude of their magnetic field, are the consequences of that field for matter and radiation in their environment. At distances of hundreds of kilometers from a magnetar, the magnetic field is intense enough to polarize the quantum vacuum. X-ray photons traveling through that field experience a different refractive index depending on their polarization, an effect predicted by quantum electrodynamics, but which only becomes appreciable at this field intensity. Observations from the XMM Newton satellite of the magnetar RxJ 185 6.5 minus 3754, published in 2017, found precisely this polarization in the emitted X-rays, the first direct observational confirmation of quantum vacuum birefringence. The vacuum of space in the vicinity of a magnetar behaves like a birefringent crystal. At even shorter distances from the magnetar's surface, the magnetic field reaches intensities where ordinary quantum electrodynamics predicts effects that have no classical analog. Above approximately 4.4 times 10 to the power of 13 Gauss, the magnetic field can spontaneously create electron-positron pairs from the quantum vacuum, a process analogous to the Schwinger effect, but here activated by the magnetic field instead of the electric field. In the magnetosphere of the most intense magnetars, pair creation is so frequent that it forms a dense fog of electron and positron plasma that interacts intensely with the radiation emitted by the surface, shaping the observed spectrum in ways that theoretical models do not yet fully reproduce. The energy that fuels magnetar bursts comes directly from their decaying magnetic field. As a magnetar's magnetic field weakens over time, the energy stored in that field is released discontinuously through stresses in the neutron star's crust. The crust, as we have seen, is an extraordinarily rigid, crystalline solid, but not perfectly rigid. The magnetic field exerts forces on the crust through conducting electrons. And when those accumulated forces exceed the material's elastic limit, the crust undergoes what physicists call starquakes, sudden fractures that redistribute energy in tenths of a second. The observable result is a burst of X-rays or gamma rays lasting from tenths of a second to seconds, with a luminosity that can exceed in 1 second the energy the Sun emits in 100,000 years. On December 27, 2004, the Earth was swept by the most intense burst ever recorded from outside the solar system. The magnetar SGR 1806-20, located approximately 50,000 light-years away on the other side of the galactic center, suffered a starquake that released in a tenth of a second an energy comparable to what the Sun emits in 250,000 years. Despite being 50,000 light-years away, the burst ionized the Earth's ionosphere in a detectable way, disrupted radio satellite navigation, and saturated all orbiting gamma-ray detectors designed for cosmic events. If the same event had occurred 10 light-years away, the radiation flux would have been sufficient to destroy the ozone layer and sterilize the planet's surface. Magnetars are not just astrophysical curiosities, they are the most energetically violent objects in the known universe, with the exception of black hole collisions and neutron star mergers. Glitches. When neutron stars leap. Pulsars, as we have seen, are the most precise clocks in the universe. Their pulses arrive with a regularity that physicists can predict years in advance. But every now and then, that regularity is interrupted in a sudden, small, but perfectly measurable way. The pulsar's rotation period suddenly decreases, the neutron star speeds up and then resumes its gradual deceleration as if nothing had happened. These events are called glitches, and they are one of the most revealing phenomena regarding the physics of the interior of neutron stars. The first glitch was detected in 1969 in two young pulsars almost simultaneously, Vela and Crab. Since then, more than 500 glitches have been recorded in over 100 different pulsars. The magnitudes vary enormously. Some glitches change the rotational period by 1 part in 10 to the power of 9, a change almost imperceptible without high-precision observations, while the largest glitches change the period by 1 part in 10 to the power of 6, still minuscule in absolute terms, but gigantic in terms of the usual stability of these objects. The Vela pulsar, the most active in terms of glitches, suffers one of the largest known events approximately every 2 or 3 years, with a regularity that is itself a subject of study. The physical explanation for glitches is one of the most debated topics in neutron star physics, and any convincing explanation must involve the neutron superfluid inside the star. The most accepted model proposes that the superfluid in the inner crust rotates faster than the solid crust surrounding it. This occurs because the superfluid cannot lose angular momentum in the same way as the solid crust. The zero viscosity of the superfluid means there is no friction to couple it directly to the crust's deceleration produced by the emission of electromagnetic radiation. The superfluid maintains its rotation speed while the crust progressively slows down. Vorticity in a superfluid cannot be freely distributed. It is quantized into microscopic-sized vortices, analogous to the vortices that form in rotating superfluid helium. These quantized vortices pin themselves to the defects of the solid crust's crystalline lattice, and it is precisely this pinning that prevents the superfluid from losing angular momentum at the same rate as the crust. As the difference in angular velocity between the superfluid and the crust increases, the stress on the pinning points also increases. When that stress exceeds the breaking limit of the pinning, the vortices detach collectively, and the superfluid's angular momentum is suddenly transferred to the crust, accelerating it in the observable glitch. It is a sudden discharge of energy accumulated over months or years, analogous to an earthquake, but caused by the quantum mechanics of a superfluid rather than the geology of a lithosphere. Glitches are also tools for studying properties of the interior of neutron stars that would otherwise be inaccessible. The magnitude of a glitch and the speed with which the pulsar recovers its previous rotation period, a process called recovery or relaxation that can last days or weeks, depend on the fraction of the superfluid's angular momentum participating in the event, the effective viscosity of the coupling between the superfluid and the crust, and the mass distribution between the star's crust and core. By comparing models of these properties with observations of multiple glitches in the same pulsar over years, astrophysicists can infer parameters of the star's interior that cannot be measured in any other way. It is high-density nuclear physics performed with astronomical radio data, a marriage of disciplines that would be difficult to imagine without these extraordinary objects. Mergers. When two neutron stars collide. August 17, 2017 was one of the most extraordinary days in the history of astronomy. At 12 hours, 41 minutes and 4 seconds Coordinated Universal Time, the gravitational wave detectors LIGO Hanford and LIGO Livingston in the United States and the Virgo detector in Italy recorded a 90-second long gravitational wave signal coming from the direction of the galaxy NGC 4993 130 million light-years away. It was event GW170817, the first detection of gravitational waves from the merger of two neutron stars. 17 seconds after the gravitational signal, the Fermi satellite detected a short gamma-ray burst from the same direction. In the following hours and days, dozens of telescopes on the ground and in space pointed toward that position and found, for the first time in history, the optical source of a kilonova, the explosion that occurs when two neutron stars merge. To understand why that day was so extraordinary, it is necessary to understand what happens when two neutron stars in a binary system merge. Two neutron stars in mutual orbit gradually lose energy and angular momentum through the emission of gravitational waves. Perturbations in the curvature of space-time that travel at the speed of light and carry energy away from the system. As the orbit shrinks and the stars get closer, the gravitational waves become more intense and the orbit shrinks faster in a positive feedback process that ends in the merger of the two stars within tenths of a second. The final milliseconds before the merger, when the two stars are just a few kilometers apart and orbiting at a significant fraction of the speed of light, produce the most intense gravitational wave signal of the event, the so-called chirp, because the frequency of the waves progressively increases up to the point of merger, like the chirping of a bird. What occurs immediately after the merger is a matter of active research and debate. The two most likely possibilities are that the combined mass of the two stars exceeds the maximum limit for a neutron star and immediately collapses into a black hole, or that the combined mass is small enough for the resulting neutron star to be temporarily stabilized by its extreme rotation, existing as a rotating hypermassive or massive neutron star for milliseconds to seconds before finally collapsing into a black hole, or, if the equation of state of nuclear matter allows it, surviving as a stable neutron star. Determining which of these scenarios occurs in each merger and under what conditions is one of the most active questions in gravitational wave physics. The kilonova produced in GW170817 provided definitive answers to a question that astrophysicists had been debating for decades: the origin of the heavy elements in the universe. Iron, nickel, and cobalt are produced in ordinary stellar nucleosynthesis and in supernovae, but elements heavier than iron, those produced through the rapid capture of neutrons by atomic nuclei, the so-called OR process, required an environment with an extraordinarily intense neutron flux that no known astrophysical process seemed capable of producing in sufficient quantities. Some theories pointed to supernovae, others pointed to neutron star mergers, where the material ejected during the merger is extraordinarily rich in free neutrons. The spectrum of the GU170817 kilonova, observed in the days and weeks after the event, showed exactly the signatures of heavy R process elements that were expected if the merger of neutron stars was the source: strontium, barium, lanthanides, and actinides in quantities that required a production of gold and platinum of between 10 and 100 times the mass of the Earth in a single event, the gold in wedding rings, the platinum in car catalysts, the uranium in nuclear reactors, All these elements were produced in significant quantities in neutron star mergers similar to GW170817 throughout the history of the galaxy. Gravitational wave astronomy had solved in a single day a mystery of cosmic nucleosynthesis that had remained open for decades. Fast radio bursts, the newest mystery. In 2007, astronomer Duncan Lorimer, reviewing archival data from the Parkes radio telescope in Australia, found something no one had seen before. A radio flash lasting only a few milliseconds, extraordinarily bright, which had arrived from a direction outside the galactic plane. The signal had all the characteristics of being of extragalactic origin. Its dispersion, the delay that lower frequencies experience relative to higher ones as they propagate through interstellar plasma, was too large to be caused solely by the gas of the Milky Way. It was a signal that had traveled billions of light years. It had been produced in a fraction of a millisecond, and in that time it released an energy comparable to what the Sun emits in days. Lorimer called it a fast radio burst, or FRB. The universe had just revealed a completely new phenomenon. For years, the astronomical community debated whether Lorimer's burst was an artifact, an interference signal of terrestrial origin, or a real astrophysical phenomenon. In 2013, confirmation arrived with the discovery of 4 additional FRBs in the same Parkes data archive, all with the same extragalactic dispersion pattern. In the following years, with the operational start of more sensitive radio interferometers like KIME in Canada and ASCAP in Australia, FRBs went from being rare curiosities to being detected at a rate of several per day, and the current catalogue exceeds 1,000 events. It is estimated that thousands of FRBs occur across the entire sky every day. The first major surprise from the systematic study of FRBs was the discovery that some of them repeat. FRB2 012-1102A, nicknamed the Repeater, was the first to show multiple bursts originating from the same position in the sky. This was crucial because it allowed its position to be localized with enough precision to identify its host galaxy, an irregular dwarf galaxy about 3 billion light-years away, and within it, a region of active star formation. The repeater emits radio bursts with an activity that varies considerably. Sometimes there are dozens of bursts in a few hours, sometimes silence for weeks. In some periods, it shows a periodicity of about 16 days, with 4-day activity windows followed by 12-day silences. A periodicity that could be due to the precession of the source or modulation by a stellar companion in orbit. The physical cause of FRBs remains a matter of debate, although the most widely accepted hypothesis currently involves magnetars. On April 28, 2020, this debate was decisively transformed when the KIME telescope detected an FRB coming from within the Milky Way itself, located in the direction of the magnetar SGR 1935+2154. It was the first time an FRB could be associated with certainty to a specific known source, and that source was a magnetar. The radio burst from the galactic magnetar was thousands of times less bright than extragalactic FRBs, but that difference in brightness can be explained by the difference in distance. Extragalactic magnetars, if they are energetic enough, could produce similar events that from billions of light-years away would be indistinguishable from observed FRBs. The model of the magnetar as the source of FRBs received extraordinary support from that observation. But the story of FRBs is not closed. Not all FRBs repeat, which could mean there are two different populations of sources. Repeating and non-repeating FRBs show differences in their statistical properties that could indicate different physical mechanisms. Some FRBs show extraordinarily complex time structures with multiple peaks within microseconds, requiring extremely small source sizes and extremely efficient energy emission, and the environment in which FRBs are produced, inferable from the signal's polarization and dispersion, varies enormously between sources, with some FRBs showing extraordinarily dense and turbulent magnetic environments. The universe of FRBs is rich enough to keep the radio astronomy community busy for decades. The precise localization of FRBs has been one of the most important technical advances in recent years. The first FRBs detected had uncertain positions in the sky spanning entire degrees, making it impossible to associate them with any specific galaxy. With the development of high angular resolution radio interferometers such as the VLBI, Very Long Baseline Interferometry, and the use of antenna arrays like the Australian Square Kilometre Array Pathfinder, it has been possible to localize several FRBs with millisecond precision, enough to identify their host galaxy and, in some cases, their position within that galaxy. The results have revealed that FRBs come from a remarkable diversity of galactic environments: spiral galaxies, elliptical galaxies, dwarf galaxies, active star-forming regions, and low-activity regions. This diversity of environments is one of the strongest arguments for the existence of multiple production mechanisms, or at least for considerable diversity within the magnetar mechanism. One of the most intriguing properties of repeating FRBs is the presence of extremely high and variable rotation measures. The rotation measure is the angle of rotation of the radio signal's polarization plane as it propagates through a magnetized medium, and it is proportional to the product of free electron density and the magnetic field component along the line of sight, integrated along the path from the source. FRB 2012110-2A, the first known repeater, has a rotation measure that varies by factors of several between different bursts and, at certain times, was the highest rotation measure recorded for any extragalactic source. That variability on timescales of days implies changes in the source's immediate magnetic environment that are difficult to explain without a compact object in an extraordinarily turbulent environment, possibly within a young supernova nebula region or in the vicinity of an intermediate mass black hole. FRBs are not just energy sources, they are probes of the environment in which they live. The equation of state, the great unsolved problem. At the heart of neutron star physics lies a question that lacks a definitive answer and connects observational astrophysics with experimental nuclear physics and theoretical quantum chromodynamics. What is the equation of state of matter at nuclear and supranuclear density? The equation of state is the relationship between pressure, density, and temperature of matter inside the neutron star, and it determines practically everything observable. The radius of the star for a given mass, the maximum mass it can support before collapsing into a black hole, the frequency of the star's fundamental mode, oscillations, and the gravitational waves it emits, and the exact moment of merger in the collision between two neutron stars. The problem is that quantum chromodynamics, the fundamental theory of the strong interaction that governs the behavior of the quarks and gluons that compose nucleons, is extremely difficult to solve in the density regime of neutron stars. At low densities, such as those of ordinary atomic nuclei, effective nuclear physics calculations can reproduce experimental observations well. At very high densities, comparable to several times nuclear density, perturbative quantum chromodynamics can work because quarks become asymptotically free. But in the intermediate regime, which is precisely the regime inside neutron stars, no existing calculation method can solve the theory with sufficient precision. The range of equations of state compatible with known physics is enormous, and different equations predict neutron star radii that differ by several kilometers for the same mass. Astronomical observations are beginning to systematically narrow down that space of possibilities. The most powerful method currently available is the combination of mass and radius measurements of individual neutron stars with gravitational wave signals from mergers. The masses of neutron stars in double pulsar binary systems can be measured with extraordinary precision through pulse timing. The highest mass known with certainty is that of PSRJ 0740 plus 6620 at 2.08 solar masses, measured with a precision of parts per hundred. This measurement already rules out all equations of state that predict a maximum mass lower than 2 solar masses. Radii are more difficult to measure. The NICER mission, Neutron Star Interior Composition Explorer, installed on the International Space Station in 2017, was specifically designed to measure neutron star radii through modeling the light curve of hotspots on their surface. Results published in 2021 for PSRJ 0030 plus 0451 and PSRJ 0740 plus 6620 place the radii of these neutron stars at approximately 12 to 13 kilometers, a range that already eliminates the softer equations of state, those predicting smaller stars. The combination of those radius measurements with mass measurements, plus the constraints from the W170817 gravitational waves, is beginning to converge toward an equation of state that is compatible with all data simultaneously. The most surprising result emerging from this convergence is that the equation of state of neutron matter seems to be surprisingly stiff, more so than many theoretical models predicted. A stiff equation of state implies that pressure increases rapidly with density, which produces neutron stars of larger radii for a given mass. This, in turn, limits the amount of exotic matter, free quarks or kaon condensates, that can be present in the core. Because those phases tend to soften the equation of state, it is possible that the interior of neutron stars is, after all, primarily neutron and proton matter at supernuclear densities without a phase transition toward free quark matter. Or it is possible that quark matter exists but in a stiffer phase than simple models predict. Resolving this ambiguity will require dozens of additional mergers detected by next-generation gravitational wave interferometers, the Einstein telescope in Europe and the Cosmic Explorer in the United States, which are designed to be 10 to 100 times more sensitive than the current LIGO. Quark stars. Is there a next step? The physics of neutron stars has a step beyond which speculation becomes theoretically consistent but observationally unconfirmed. The possibility that compact objects exist composed not of neutrons but of deconfined free quarks If the density in the core of a massive neutron star exceeds a critical threshold, theory predicts that neutrons should dissolve into their constituent quarks, producing a phase of quark matter that could be the most stable state of matter at those densities. The most fascinating possibility, originally proposed by physicist Edward Witten in 1984, is the so-called strange matter hypothesis. That matter composed of U, D, and S quarks in equal proportions, called strange matter, could be the lowest energy state of matter in general, more stable even than ordinary ion. If this were correct, it would have extraordinary cosmic consequences. Any piece of ordinary matter that came into contact with strange matter could be catalytically converted into strange matter, a process that would propagate through matter at speeds near the speed of light. A ball of strange matter the size of an atom, called a strangelette, could in principle convert the entire Earth into strange matter in a fraction of a second. This scenario, known as the strange matter apocalypse, was taken seriously enough in the early 2000s for the CERN Safety Review Committee to evaluate whether collisions in the LHC accelerator could produce strangelets. The conclusion was that even if strange matter is the most stable state, the production of strangelets in colliders is so improbable and the conversion rate so slow that it represents no risk. High-energy cosmic rays, much more energetic than any terrestrial collider, have been bombarding the Moon and other solar system objects for billions of years without producing any observable conversion. If strange matter were as catalytically aggressive as the most pessimistic scenario suggests, it would have already happened. But if strange matter exists and is stable, there could be compact objects composed of it. Strange quark stars. A strange quark star would have slightly different observational properties than a conventional neutron star, a smaller radius for the same mass, a surface composed of strange quarks instead of a neutron crust, and the absence of the solid crust that produces glitches in pulsars. Some researchers have proposed that certain pulsars with properties difficult to explain with the conventional neutron star model could be quark stars. The debate continues, and definitive resolution will require radius measurements with enough precision to distinguish between the predictions of neutron star models and quark star models for the same mass value, a task that the NICEA mission and future X-ray missions are beginning to address. The limit with the abyss. Low mass black holes. There is a frontier in the physics of compact objects that is at once perfectly defined in theory and extraordinarily fuzzy in practice. The limit between the most massive neutron stars and the least massive black holes. Theory predicts that a maximum mass exists for a neutron star, the Tolman-Oppenheimer-Volkoff limit, above which no degeneracy pressure can oppose gravity and the object must collapse into a black hole. But the exact value of that limit depends on the equation of state of matter at supernuclear density, which, as we have seen, we do not know with sufficient precision. Observations suggest that the limit lies somewhere between 2 and 3 solar masses. The most massive known neutron stars, such as PSRJ 0952-0607 with 2.35 solar masses, are approaching that limit. The least massive known black holes, typically formed in X-ray binary systems, tend to have masses of 5 to 10 solar masses, leaving a gap of approximately 2 to 5 solar masses between the most massive compact objects and the least massive black holes. This gap was for a long time a mystery. Is it a real absence of objects in that mass range, or is it an artifact of observational biases? The GW190814 event, detected by LIGO and Virgo in August 2019, highlighted the depth of this uncertainty. The gravitational wave signal was interpreted as the merger of a 23 solar mass black hole with a 2.6 solar mass object. The 2.6 solar mass object is in the gap. It is too massive to be the most massive known neutron star, but too light for typical black holes. Was it an extraordinarily massive neutron star? Was it a low-mass black hole? The answer would determine whether neutron stars can reach masses of 2.6 solar masses, which would strongly constrain the equation of state, or whether black holes can form with such low masses, which would imply a different formation mechanism than standard stellar collapse. The frontier between the densest objects and black holes is not just a problem of taxonomic classification. It is the frontier where known physics reaches its own limits of validity. A neutron star is an extraordinarily extreme object, but it remains an object with a surface, with matter that can be studied through its radiation, with properties that can be compared with physical models verifiable in the laboratory. A black hole is something qualitatively different. It has no surface in the ordinary sense. It does not emit radiation from its interior, and the singularity at its center is the place where the equations of general relativity cease to be valid, and a theory of quantum gravity, which does not yet exist, would be necessary. The neutron star is on this side of the abyss, the black hole is on the other side, and the frontier between them is one of the most fascinating places in theoretical and observational physics. The observational tools available to study this frontier are multiple and complementary. Gravitational wave detectors provide the most direct mass measurement at the moment of merger, regardless of whether the object emits light or not. X-ray telescopes allow the study of binary systems where a neutron star or a black hole accretes material from a stellar companion, with difference in the spectral signature that in principle allow for distinguishing between the two types of compact objects. Radio telescopes allow for the detection and precise measurement of pulsars, when the geometry of the system favors the detection of radio beams. And the Event Horizon Telescope network of radio telescopes, which in 2019 captured the first direct image of the shadow of the supermassive black hole in M87, is being expanded with the long-term ambition of resolving the internal region of stellar mass compact objects in our galaxy. In that future, the frontier between neutron stars and black holes will cease to be a statistical inference and will become a direct image. GPM-J 1839-10, the object that defies categories. In 2022, astronomers working with the Murchison Wide Field Array in Australia announced the discovery of a radio source that emitted pulses every 22 minutes with a stability and regularity that did not fit into any known category of astronomical object. The source, named GPM-J 1839-10, had been emitting that signal since at least 1988, when it appeared in archival radio telescope data that no one had examined in search of signals with such a long period. 3.5 decades of regular emission with a period of 22 minutes without any previous detection, because no search system was designed for such long periods. The problem with GPMJ1839-10 is that a period of 22 minutes is incompatible with standard models of what a radio-emitting neutron star can be. Pulsars emit radio waves because the rapid rotation of the star, combined with its intense magnetic field, creates the conditions for particle acceleration and the emission of coherent radiation at the magnetic poles. But there is a deadline, a threshold in the period versus period derivative diagram, beyond which it was expected that no pulsar could maintain radio emission. The rotation is too slow to maintain the voltage necessary for particle acceleration. GPMJ1839-10 with its 22-minute period is deeply beyond that deadline. It should not be emitting radio waves, and yet it does. The hypotheses proposed to explain GPMJ1839-10 include a neutron star with an extraordinarily intense magnetic field on the order of 10 to the 15 Gauss, an extremely slowly rotating magnetar whose magnetic field is so intense that it could maintain radio emission even at such long periods. Another hypothesis proposes that it is a white dwarf with a very strong magnetic field, a type of object that can emit radio waves under certain conditions and that naturally has longer rotation periods than neutron stars. A third, more speculative hypothesis involves a binary system where the radio emission is related to the interaction between the two objects rather than the rotation of just one. What makes GPMJ1839-10 particularly significant is not just its individual mystery, it is that its discovery revealed there is a population of long-period objects that radio astronomy has been systematically ignoring because search systems were not designed to detect them. In 2023, a second similar object was announced, GPMJ0901-4046, with a period of 8 seconds. In 2024, a third candidate. Each new discovery suggests that these objects are more common than previously thought, and that the history of neutron star astrophysics is far from complete. The universe continues to reveal that the categories we construct to organize our understanding are always provisional, always susceptible to being broken by an object we are not looking for. Gravitational waves and the future, what we still do not know. The detection of gravitational waves in 2015 opened a new window to observe the universe, and neutron stars have proven to be some of the most information-rich objects that this window can reveal. The first detection of gravitational waves from the merger of two neutron stars in 2017 and the dozens of candidate detections in subsequent observational cycles of LIGO and Virgo have already generated significant constraints on the equation of state of dense matter. But the future of neutron star gravitational wave astronomy is even more ambitious. The Einstein telescope, currently in an advanced design phase with construction expected to begin in the mid-2020s and first scientific observations in the late 2030s, will be a triangular-shaped underground facility with 10-kilometer arms instead of the 4-kilometer arms of LIGO. Its sensitivity will be between 10 and 100 times greater than that of current detectors, allowing it to detect neutron star mergers at distances of billions of light years instead of the hundreds of millions of light years accessible to LIGO. The number of mergers detected per year could go from dozens to thousands, providing statistics that will transform the precision of constraints on the equation of state. The detection of gravitational waves from continuous sources is another goal for the future. A neutron star that does not rotate perfectly axis-symmetrically with a bulge or a deformation in its shape will emit continuous gravitational waves at a frequency equal to twice its rotation frequency. The amplitude of these waves depends on how deformed the star is, and the maximum possible deformation depends on the stiffness of the solid crust. If the crust is sufficiently rigid, the deformation could be detectable with next-generation detectors. The detection of continuous gravitational waves from a neutron star would provide direct information on the elastic properties of the crust, complementing the information about the deep interior obtained from mergers. The Pulsar Timing Array program, which uses networks of millisecond pulsars as distributed detectors of very low-frequency gravitational waves, produced in 2023 the first statistically significant evidence of a gravitational wave background originating from supermassive black hole binaries in the distant universe. This result, announced simultaneously by 4 independent collaborations, marks the beginning of nanohertz gravitational wave astronomy, a completely new window that is complementary to that of LIGO and will become more powerful over time as new pulsars are added to the array and observations accumulate over decades. Beyond gravitational waves, the future of neutron star physics involves next-generation X-ray telescopes, especially the Chinese-European EXTP and the proposed STROBE X in the United States, which will perform hot spotlight curve measurements with a sensitivity that will exceed NICER by an order of magnitude, reducing uncertainties in neutron star radii to the level of tens of meters instead of kilometers. At that level of precision, the distinction between different equations of state will be definitive for most existing models. Stranger than we ever imagined. We have come a long way from the first description of what a neutron star is to the most recent mysteries of long-period objects and gravitational wave backgrounds. At each stage of the journey, we have found that the reality of these objects surpasses in strangeness and richness any previous expectation. It is time to wonder why, and to attempt to articulate what the physics of neutron stars tells us about the universe and about the limits of our knowledge. The first reason why neutron stars are stranger than we ever imagined is that they are convergences. Within a single city-sized object, several fields come together. General relativity, which describes the curvature of space-time under the action of gravity and without whose relativistic corrections one cannot even predict the correct period of a pulsar. Quantum mechanics, which governs the behavior of electrons and neutrons in the crust and produces the degeneracy pressure that prevents collapse. Nuclear physics, which determines the interactions between nucleons in the core and needs to be extrapolated to densities where it has never been directly verified. And particle physics, specifically quantum chromodynamics, which could be relevant in the deepest core if quarks become deconfined. No other object in the universe brings all these physical regimes together in such a small space. Neutron stars are laboratories of unified physics that no particle accelerator could replicate. The second reason is the speed at which we continue to discover new phenomena. Pulsars were discovered in 1967. Magnetaries were not identified until the 1990s. FRBs were not discovered until 2007. Long-period objects were not detected until 2022. Each of these categories required a different observation technique, a different telescope design or data analysis method, and in some cases, a prior theoretical idea that allowed for searching in the right place. What this tells us is that the phenomenology of neutron stars is considerably richer than any fully developed theoretical model can capture, and that future discoveries will continue to surprise those working in this field. The third reason is the connection to the universal. Neutron stars produce the heavy elements that make up the matter we are made of. They produce the most intense magnetic fields in the universe. They accelerate particles to energies that no human accelerator can reach. They disturb space-time with waves that can be detected 1 billion light-years away. They are local objects in the sense that they are within our galaxy, accessible to detailed observation, and at the same time, they are universal objects in the sense that the processes occurring within them have cosmic consequences that affect the chemical composition of the entire universe. The fourth reason is the most difficult to articulate, but perhaps the most important to understand. Neutron stars remind us that nature is not obliged to respect our intuitions. When physicists derived the equations of general relativity in 1915, the Schwarzschild solution that predicts black holes was considered for decades as a mathematical curiosity without a physical counterpart. When quantum mechanics predicted electronic degeneracy pressure in the 1920s, the idea that such pressure could support an Earth-sized object with the mass of the Sun seemed like science fiction. When Duncan and Thomson proposed magnetars in 1992, magnetic fields of 10 to the 15 Gauss were so different from any field producible in a laboratory that the credibility of the proposal depended entirely on the strength of the theoretical argument. In each case, nature turned out to be doing exactly what physics predicted, even when those predictions seemed impossible from the perspective of everyday experience. This is, at its core, the greatest story that neutron stars have to tell. It is not the story of extreme objects in a remote corner of the universe. It is the story of physics as an enterprise of understanding, the story of how rigorous thought, combined with careful observation, can reveal realities that no intuition could reach on its own. Every new property of neutron stars that has been predicted and then observationally confirmed is a validation that the equations we use, derived in laboratories at temperatures of a few hundred degrees and magnetic fields of a few Teslas, remain valid in conditions that differ by dozens of orders of magnitude. That was not obvious. That it is true, it's one of the most extraordinary observations of modern science. But the story is not finished. The equation of state of matter at supernuclear density remains unknown with precision. The exact mechanism of FRBs remains uncertain. The nature of long-period objects is an active mystery. The possibility of quark matter in the cores of the most massive neutron stars remains an open question, and somewhere in the sky, in some telescope that has not yet been built, or in some data archive that has not yet been analyzed with the proper tools, there is a neutron star about to reveal something that no one expected. Something that will require model revisions, calls to colleagues, data reviews. Something that, upon being finally understood, will once again expand our notion of what the universe allows. In 1967, Jocelyn Bell saw in her radio data a signal that pulsed every little more than a second and had no name because the object producing it was unknown. Today, more than half a century later, we know that this signal came from a rotating neutron star, an object of a density comparable to that of an atomic nucleus, with a magnetic field of billions of Gauss, with an interior of superfluid neutrons and a solid crystalline crust stiffer than the hardest steel we have ever manufactured. We know that there are thousands of similar objects in the galaxy, that some of them spin 600 times per second, that others have magnetic fields that polarize the quantum vacuum, and that when two of them collide, they produce the gold of the universe. That is, the distance science has traveled since that first mysterious signal, and yet, with each passing year, the universe reminds us that there is more to discover. Neutron stars are stranger than we ever imagined, and they will be even more so than we imagine today.